So in the previous portions of the video, I feel as though I may have been remiss in not mentioning sort of the names of some of the archetypes of angular momentum questions. So one of them is the collision, where you have a projectile colliding with a system that can rotate. Very often those look like this, where you have something like, all right, here's an object, it's going to go crunch into the other one. And then the tricky thing is you got to remember that the moment of inertia now includes all of the things that are rotating, including the projectile. They won't always look like this, but that's one way that they frequently look. All right, so that's the projectile colliding with a system. All right, the other major archetype is called the deformable system. In the deformable, and I'll put a name on this one, the deformable system has a system where components of it are capable of moving around. So one place where you have actually seen the deformable system, I presume, is in what we literally call the figure skater problem. So here we have figure skater. In the figure skater problem, as it's sort of classically represented, right, you have obviously a figure skater, right? She's initially spinning, or I suppose he, right, with arms out, okay, maybe even one leg out, as I've drawn here, and is already spinning, and then pulls the arms and maybe the other leg in. Now, the way that moment of inertia works, if you recall, is mr squared, basically, right? Everything's proportional to mr squared. Meaning if you take mass and it's located further from the pivot, you have a greater moment of inertia. If it's located closer to the pivot, then you have a smaller moment of inertia. So what the figure skater has done is moved the mass, which is to say arms and legs, right, in closer to the pivot. And that means that the moment of inertia has dropped. And the result then is going to be that the angular velocity must increase. All right, so that's often how a deformable system kind of question is going to go, is there's a change in the moment of inertia because the system can rearrange. And then as a result of that increase or decrease in the moment of inertia, there will be an opposite increase in the angular velocity. All right, so these are two major archetypes of questions. All right, now on to the matter at hand. This is example 8, so find that one in your notes packet. So to answer part A, the moment of inertia of the merry-go-round that this child is contemplating, really all we need to do is reference the correct moment of inertia equation. It says that the merry-go-round, or I think we can presume the merry-go-round is going to be a solid cylinder. There it is. Okay, now we find its angular momentum. In this case, the appropriate equation to use is not mv cross r, but I omega. It's a rotating solid. It has an angular velocity. So if we plug in the angular velocity of 2 and my previously calculated moment of inertia, we would get 400. 400 what? Well, okay. The units for moment of inertia, you will notice, were kilogram meters squared. That's based on the units for m is kilograms, r is meters, and it's squared, so kilogram meters squared. Okay, so if I have kilogram meters squared for I, and omega is radians per second, my units are going to be kilogram meters squared. For some reason, they drop the radians and just say per second. Now, why they drop the radians, you may understand later, but radians is like barely a unit. Also, though, if you look at the other equation for angular momentum, mv cross r, and puzzle out the units there, you'll see how you get kilogram meters squared per second. All right, now the child drops onto the merry-go-round. Okay, all right. Now, if right now you're thinking, okay, kid is like a particle, he's colliding with the merry-go-round, I'm going to use mv cross r. Sort of. The reason that we end up not needing to care about that is because when the kid collides with the merry-go-round, he's going to be moving like that. And angular momentum is not going to be conserved along that axis because, brace yourselves, the merry-go-round is not free to rotate like that. Okay, I think we can all agree that because it's on the ground or not in space, the merry-go-round can't rotate like that. So we don't actually need to act as though the child contributes any angular momentum to the system. He really doesn't, because he's just dropping straight down onto it. Instead, all he's doing is adding more to the moment of inertia. So it ends up acting as though this is a deformable system, because you have an initial I and omega, and afterwards we have a new moment of inertia, because the kid is on the merry-go-round now, and therefore we will have a new angular velocity. So it's like a collision where you just add additional mass, or in this case, inertia, moment of inertia. The left side we already calculated to be 400. The right side, we still have to figure out the new moment of inertia. The relevant information about the child is where he lands, and also that the child is 20 kilograms and that we're supposed to treat him like a point mass. So there's my rough diagram of what the system looks like after the kid lands on it. Okay, so moment of inertia of the merry-go-round is 200. That's just the merry-go-round, MGR for merry-go-round. However, we also have the child. A point mass is calculated using just mr squared. Note, though, that the r here is not the radius of the merry-go-round, it's where the kid is located, which is 0.5 meters from the pivot. All right, so really the child doesn't change the moment of inertia of the playground by all that much. All right, so now we got 205 there and times omega 2. Okay, and my apologies, actually, that was 205 there. That was the answer to C. That's all C wanted to know, is the new moment of inertia. So really what I'm doing here is D. D wants to know the new angular velocity. Okay, so a little bit of math later, and the new angular velocity is roughly 1.95 radians per second. All right, so it was moving at 2, now it's moving at 1.95. Didn't slow down that much. Okay, now continuing the story, the child now rolls to the outside edge of the merry-go-round. Well, why would that matter? Well, okay, if you think about it, right, here's the child initially, right, pretty close to the center. As the kid moves out, it's actually sort of like the opposite of the figure skater problem. You have mass that is now moving away from the pivot. As mass moves away from the pivot, the moment of inertia of the system is going to go up. So the child is now going to have a much, much larger effect on the moment of inertia than they had before. Before, they were only contributing 5 kilogram meters squared. But in a moment, we're going to see that when they are located on the outside edge of the system, they are going to have an enormous effect on that moment of inertia compared to what they had before. All right, so your answer for this one, how does the angular velocity of the system change? He's moving outwards. The moment of inertia is therefore increasing as his distance from the pivot goes up. Therefore, based on what we know, if the moment of inertia goes up, the angular velocity should go down. The angular velocity will go down as the child rolls to the outside edge. Now, it doesn't explicitly say to do this, but I'm going to do it because I think it's important. You need to be able to talk about, all right, what is the final angular velocity as the kid rolls off the edge. So as the kid rolls off the edge, the final moment of inertia, as I shall call it, is, all right, well, we still have a merry-go-round, 200. But the child has a new contribution to the moment of inertia of, all right, mr squared is our formula, but r is now 2. All right, so that's going to give us now 80. Therefore, the final moment of inertia as the kid rolls off the edge is 280. All right, so using still the deformable system model, our initial angular momentum was 400. What, still? Mr. Errico, that's what you used up in part B. Yeah, still. The point of conservation is that something's not changing. If I said angular momentum's conserved, then it's conserved. That means it's still the same. The angular momentum didn't change. It was 400 before the kid landed on it. Now it's still 400 after he did land on it, and it's still going to be 400 ultimately when he rolls off of it. All right, but of course it's going to be much, much smaller now. The final angular velocity is roughly 1.43 radians per second. All right, now when they're talking about the changes in energy, I'm not going to explicitly work that out because I think this video is probably long enough. However, if you want to talk about what those changes in energy are that occur, energy is not conserved during this process. Work is going to be done. Energy the kinetic energy of the system can increase or decrease depending on exactly what this child does. So do not assume that the kinetic energy is the same before and after, okay? For example, you should calculate it, right? What is K rotational at the start, the very start? Plug in the numbers, 1/2 I omega squared. See what you get when that's I, 200, and omega was 2, all right? And then look at what is it now a little while later when the kid has landed on it and it has slowed down slightly. It's going to be a little bit less. And then, again, calculate it all the way at the very end when the moment of inertia is 280 and the angular velocity is 1.43, you will find it has once again decreased. All right? So I'm not going to calculate it for this video, but you can calculate it on your own and see how that kinetic energy changes. Please note, it's not always going to decrease. If the kid had done something like land on the outside edge and then rolled inwards, during the part where he rolls inwards, the kinetic energy would increase as the moment of inertia drops and the system spins faster. So in the figure skater question, for example, when the figure skater tucks her arms in, there's more kinetic energy than there was before because she's spinning faster. All right, well, I hope that helps with the concept of angular momentum. Thanks for watching.